Right. Now, today, those who really want to join 5443, please join, because today this will be an introductory session. I'm not planning to do that much today, but I'll be doing fair amount of extra classes for this course, like I did for last year. So, so we are going to talk about engineering hydrology. Now, before getting into the subject matter, I know there are some lateral entry students in this course. Could you please raise your hands in the system who have come to this course in lateral entry? Please raise your hand. I'm quite sure there must be lateral entry students. I mean, the students who were exempted from level 3, especially diploma holders, might have been exempted from level 3 courses, and they might have come to do the subject directly. So there is one. Please raise your hand. 1, 2, 3, 4, 5, 9. Are there any more students? 10, 11. So far 15. Okay, there are about 15 students or 16. Okay, let's see how many are there. 16. Yeah, 15. Yeah. Okay, let's say 15, 16 students are there who have come to do this course laterally. So your understanding, please lower your hands in the system. Raise down your hands. Okay, because I'll need to get your responses for other things as well. Now, so I repeated these instructions during yesterday's day school as well for 6345. Now at Open University, we are studying in a different mode. We call it ODL mode, open and distance learning, right? But what is open and distance learning? Open and distance learning is not part-time learning, right? Especially those who are employed and doing this course think that this is a part-time degree. That's a wrong attitude towards this degree. In fact, it is not part-time, it is open and distance mode. It is in open and distance mode, but you can do it during your leisure time. You will have to be fully engaged throughout the period of your study with various aspects of the study. That is what open and distance learning means. But unfortunately, some of our students, especially these lateral entry students who came directly, think that it's a part-time degree. So sometimes they carry the attitude like the attitudes of Calania external graduates. You know, when they do this external degree at the art faculties, so you just follow a few lectures and cramp the notes and come to face the exam. But if you have the similar attitude to this course, you might find it difficult to pass. For example, let me tell you, last time only 54 students were eligible to sit for the final exam for this subject, and only around 20, I have forgotten the exact number, maybe around 23 or 25 students have passed the subject. So what I found was that many of the failing students were in fact working students, and some of them have given up the course likewise. Now, during the registration, we have clearly told you that please take up the subjects which you can do during the available time you have. Now, there's no point of doing 6 subjects and getting C's. If you can do 3 subjects and get A's. Okay. Now the beauty of Open University degree is this. Now, if you go to a conventional university and you have a fixed time period, you have to complete the course during that fixed time period, and the gradings that you get within that fixed time period will decide your class. Okay, let's say within 4 years, if you get an average about 75, you will get a first class, right? Likewise, that is how they decide the class. But at Open University, the time is not a factor for class. Okay, time is not a factor for class. Let's say if you do the degree in 10 years time, and if you get ample amount of good results, you will have a better class, right? So nobody will ask whether you have completed the degree in 10 years or 8 years or 7 years. So this advantage is there at Open University. Unfortunately, our students, especially working students, they do very poor time management, and they don't understand the amount of time they have to study, and they take a fairly high amount of workload. So it is obvious that you are going to make some failures, right? So you have to keep this, you have to bear this in mind, right? So you have to allocate a certain amount of time for a day and work on them. Otherwise, I know people get together at the close to the exam. They try to do copy classes, group studying, and this sort of things will not work. Because I'm a lecturer, if you look at my papers, I check fundamental knowledge. Now, I check fundamental knowledge, sometimes not directly, indirectly. And I will also check your capacity to apply certain things, especially in this subject, especially in engineering hydrology. There are a lot of applications. You can give ample amount of sums, various type of sums. But remember, it is always based on the fundamentals that you are going to learn in this course. Nothing outside the course. I will guarantee that. Okay, that's one thing for sure, right? Then I would like to draw your attention to your coursework. Now, in this course, we have around I think there is one practical you have to do. The last time I had to give you a data sheet and do the practical, but this time I am planning to do a practical, if possible, at the field or in the lab, right? I want to do a current meter practical. I have repaired a very old current meter which we had in our department, and we are going to do the practical. We have repaired the current meter. It is in working order. So I want you to do that practical and get a sense of flow measurement. And I believe you are learning about other methods of flow measurements like weirs, plumes, things like that in hydraulic courses. Now in this course, so I'll specifically teach you about current metering, right? That's the practical you have. Please do the practical and get through it. It is compulsory. That's about your course. Let me go to your the synopsis of your course. 1 minute, please. Hope you can see the synopsis here. Now, sorry, I have taken the wrong synopsis. Okay, now this is the synopsis for engineering hydrology. You can see this. Now, if you go down, now here you can see the eligibility criteria. Now there, you need to pass lab. Average lab has to be more than 40. If not, you are going to fail. That means lab classes are compulsory. So last time we couldn't do it due to various reasons. So we did online lab session, like I send you a data set and I send you the theory and you have to do the lab report and submit. But this time around, we are planning to do it at the lab, right? And you can see the rest of the thing is not that complicated in this course. So you will have to basically pass the 2 CATs. You will have to do the lab and you will have to pass the final exam. Somebody asked about the guidebooks. I can't help you about that, but all what I can do is that I'll try to send you the session online, what we are going to do today and in coming day schools as well. I'll be sending you the sessions. Now, this is a serious problem. You can inquire it from them again, right? Don't wait until last moment. Try to intervene and inquire, because it is handled by a different department at Open University. That's called the dispatch department, right? All what we can do is ask why they have not distributed these things. Anyway, as a supporting material, I will provide you the notes on the Learn OUSL. So I'll be today I'm going to start from session 4. Now this day school we will continue like session 4, 5. Then we will move into session 1, 2, 3. Then out of first 5 sessions, there will be CAT 1 exam. Then after that, I'll talk about the remaining sessions and let's proceed with the course with CAT 2 and final exam. Okay. Right. So let me begin the presentations. I will not do that much today because there is a clash. I understand. So it's not our fault or active diary fault. It's because students have taken overwritten courses. So because of that, there is a clash. Right. I will share. Right. Hello. Can you see the screen?
Yes. See
Yes,
that.
sir.
Okay, thank you. Right. Now,
Can't hear, sir.
Can't hear, sir.
I'm sorry. Okay, I'll begin again, right? Now, this is your course. It is engineering hydrology, and its course code is CVX4241. My name is Kaila Parnavitana. I am your academic coordinator for this subject. Let's begin our discussion with water resources engineering. Well, you know that water is a finite resource which is essential for human survival. Now, without water, we can't survive, and therefore, it's a finite resource. We don't have that much of water which can be utilized by human. It's very small quantity, so that we have to manage it. In the field of water resources engineering, we always discuss about ways and means of managing water efficiently and effectively, right? What is efficiently? Efficiently means reducing wastages. Effectively means we should have certain positive results out of consumption. And if you look at the field of water resources engineering, basically it has three segments like utilization of water, water management and pollution control, then control of water. Now, when it comes to utilization of water, that means the usage of water. So we use water in these applications, in these areas. Irrigation, then domestic consumption, then we use it for industrial use, then we use it for hydropower generation. Now, these are the three main please keep your mic switch off, right? I can't keep on unmuting you, right? Right, okay. Now, utilization of water. Now, the utilization of water is basically covered in these fields: irrigation, domestic water consumption, industrial use, hydropower generation. Now, all these fields are coming under water resources engineering. Now, when it goes to water management and pollution control, you know, the water quality management, then the water for fauna and flora. Would you please mute your mics? You are disturbing the flow of the lecture. Okay, so under water management, water quality management, water for fauna and flora is discussed. Now, when it comes to water quality, it is very important to manage water quality. Otherwise, those water become inconsumable, right? Then water for fauna and flora, you know, we need to maintain the ecology in the world. Without ecology, we won't able to survive. For example, if the bees die out in the world, within 2 years, human will wiped out from the planet. So that's the coexistence or the correlation that we have with the environment. So therefore, it is very important to maintain fauna and flora. Without fauna and flora, water quality will not be maintained. Then our fish supplies will depletes, which is one of the major food supplies for humans. Then also it is one of the major supplies of various medicines and various resources. So if we deplete fauna and flora in the water, it will affect our survival. Then the other aspect of water resources engineering is the control of water. You know, we have to control water to overcome these requirement. You need to have flood control. You have to do flood control. Then you have to do land drainage. Then you also have to do sewage. Then sewage management. Then bridge construction. Especially if you want to do bridge construction, you need to have an understanding of the flow of the streams and rivers. Such things are there. So these are the basic categories of water resources engineering. So if you move further, if you look at the applications of water resources engineering, one of the major applications of water resources engineering is flood routing. And you can see, and in fact, we are going to mainly focus on this aspect in our course, because this one is the major one which will contribute to all these other aspects. So we should be able to quantify the amount of water received by a catchment and how much will it come to a certain location to investigate flood or design dams or design any other thing. Now for spillway designs, of course, this is important. Then sizing culverts or bridges. Now, for example, how many are there from RDA here? How many are? Anybody from RDA? Nobody. Okay. Right. Now, when you design culverts, you cannot just go for type drawings, because you need to have an understanding about the flow that is coming to this point to provide the adequate amount of drainage. So that amount of water that is going to come to this point has to be decided by hydrological analysis. Then if you look at simple thing like drain inlet in a road, right? If you don't provide adequate amount of drain inlets in roads, what will happen to roads? They will get flooded, right? Because they are impervious layers. So to size these drain inlets, you need to know about the hydrological applications in the area. Then when you're going to design the drainage networks, to design drainage networks, of course, you need to know about the hydrological data, how much rainwater will be there, how much percolation is there, information such as that. So let us briefly talk about water resources in Sri Lanka. Now, Sri Lanka has 3 climatic zones, which are classified based on the intensity of rainfall that it receives. So you all know about wet zone, intermediate zone, dry zone. And Sri Lanka also has 103 river basins. You can see this is the river basin map of Sri Lanka. You know, the biggest river basin of Sri Lanka is Mahaveli River Basin, which is 10,446 square kilometers. Then the other important thing in Sri Lanka is the distribution of reservoirs in Sri Lanka. Well, you can see here, there's a very high density of small, medium, and large scale reservoir distributions in Sri Lanka. You can see most of the reservoirs are built in comparatively in dry zone, right? You can see if you compare the climatic zones and the reservoir distributions, you can clearly see that. Then you can see the density of reservoirs in Sri Lanka. In certain parts, we have very high density of reservoirs. If you, especially in Wayamba, right? This area, right? It says there are 7 small reservoirs for every 1 square kilometer. I mean, in fact, this map does not show the same level of intensity, but there is a limit that we can take into a map. So that is why it doesn't show all that. So around 7,800 cubic meters of groundwater resources are there in terms of reservoirs in Sri Lanka. Now let us compare our water resources with the regional countries in the South Asia. Now, if you look at the risk levels, now I have taken this from IMI 2007, one of the reports of IMI, which was compiled in 2017, and you can see the risk level for different countries. Now, if you take Sri Lanka, the high risk level are taking place in Sri Lanka are in this case. You can see what sort of high risk disasters are there. Storms, cyclones, riverine floods, coastal floods, they are all belongs to hydrology, right? Then if you go to medium risk levels, you can see flash floods, landslide erosion, then the droughts and aquifer salination, things like that. Then when it comes to low risk level, so groundwater depletion. So you can see with respect to Sri Lanka, the subject of hydrology is very much interconnected with the disasters that we'll have to face in the coming decades, right? And in compared to other countries like Afghanistan, then especially India, if you go to India, you can see one of the major one is droughts. So we are in the opposite side of them, right? Okay, now let's get into the introduction of hydrology. Before getting here, I would like to show you a small video from YouTube. Please watch this video.
My job is to make college easier because students have a lot on their plate.
Please watch this video.
In this video, I'd like to provide a course introduction. As I mentioned in the syllabus, this course actually has 2 primary components. We have a hydrology component and a hydraulics component. And in this video, I'll be talking about what hydraulics is and what hydrology is, but I'm also going to be focusing on how the two studies are actually interconnected or interrelated. The best part is just to start with kind of a conceptual example. So let's say we have a roadway, say it's a roadway going north-south, and let's just call that a highway. So I have highway, okay? Adjacent to the highway, we have an area that we're going to designate as a watershed. And I'll label that in just a second here. Okay, so here we have a watershed. Okay, watersheds are also known as basins. Okay. Now, a watershed is actually the boundary or the delineation of a watershed is basically set so that any rain event, so let's say, for example, we have a storm, kind of like the one this afternoon. Okay. So we have a rainstorm. Within that storm, any drop of water within this watershed is going to make its way out to a point that we call the outlet. Okay. If there is a drop of rain outside this boundary, then it would basically go on in a different watershed. So again, the watershed is kind of bounded by, it's a region in which any rainfall within that region makes its way to a single outlet. Okay. Now, talking about rain, there's lots of different factors that influence the precipitation, okay, or kind of characterize the precipitation. The first thing we need to talk about is the duration, okay? Is this a storm that's a matter of minutes, or are we talking about a storm that lasts hours? Okay, and these switch markers. Another issue that we have to consider is the coverage of the storm. And what I mean by that is the rain only affecting this part of the watershed, or is it covering the entire watershed? For example, think when you've been on a highway and you're driving along and you're in a driving rainstorm, and then all of a sudden it's like you cross this magic barrier and there's no rain whatsoever. Okay, and so that's actually a huge factor, is if we have precipitation in the entire watershed or just covering a portion of it. So the coverage is a big thing. The other issue that we think about is intensity. Okay, now with intensity, what we're talking about is the difference between the storm that say you start off with a few raindrops, you're out for a walk, you feel a few raindrops, and little by little it builds up, and then it's a really strong storm, and then it kind of peters out. Versus another storm, which is common here in the South, in which with little warning, all of a sudden, boom, a lot of water, doesn't last very long, and then just kind of fades away. So that's what we mean by intensity. And we actually plot this. We can plot, sorry about that, let's see, if we plot time versus intensity, we might get a graph that looks something like this. It's usually a type of histogram. And again, each one varies in terms of its shape. In this particular one, you can see there's a gradual buildup. It reaches a peak and then kind of drops out. Some might have an intensity that's really strong at the beginning. Some might have an intensity that's really strong at the end of the storm. Okay. This graph here, we actually refer to as, I'm going to do the line here. This is referred to as a Hiatograph, and we're going to learn a lot about these in class. So right now I'm just kind of sharing with you some of the terminology. Okay, that's a Hiatograph. Okay, so that takes us actually through the first part of the course. So in hydrology, a good portion of the course is focused on on either characterizing. Let me switch markers here. This one's getting a little low. In quantifying rainfall. Okay, and I'm just going to say precip. Oops, try that. I don't have an eraser here. All right, so quantifying or characterizing precipitation. Okay, so essentially, how much did it rain? And the rain that occurred last night, was that significant of like a 5-year rain event? Was that a 10-year storm? We've all heard about these periods of storms, and that's what we mean by characterizing or quantifying precipitation. Now let's look at the watershed. Now, of course, within the watershed, it's likely that we're going to have several streams, right? And they're going to have different branches. Okay, and again, all this flow eventually is going to make its way to the outlet. Say we have a storm. Now, initially maybe the storm starts over here in the northeast corner of the watershed. And initially maybe it gets saturated, and then little by little parts of the watershed start contributing to the flow, and eventually all the flow is going to make its way to this outlet. Okay? If we actually look at that outlet, if we actually plotted that over time, we have a flow over time. Okay? And so again, initially maybe this part gets saturated, and then the runoff from here starts making its way down, and these rivers start contributing, and little by little everything contributes. And so at this point here, if we actually had a flow meter, it would actually register the flow going through that outlet. And again, it would pick up. It might start off real small because there's not a lot of areas contributing to the flow, but little by little it's all contributing. It reaches some peak flow, and then from that point on it's going to drop off once the storm eventually ceases. Okay? This right here is what we refer to as the hydrograph. Hydrograph. Okay? So that's the second part of the class in terms of the hydrology component. Is the first part is characterizing the rainfall, and the second part is understanding how the watershed's going to respond to that rainfall. So say watershed response. Okay. And again, there's a lot of factors that contribute to the watershed response. We're going to talk about those in more detail. I'm not going to put them up on the board, but you can imagine some of them are the obvious, like the size of the watershed, the slope. You know, is it a watershed in an area that's like a farmland that's flat? Is it a watershed with a lot of mountainous areas where the slope is steep, and that would influence a lot the runoff, the vegetation cover, the type of soils that we have, the condition of the soils. There's a lot of factors that go into that. Now let's talk a little bit about the hydraulics component of this course. Okay? With the hydraulics part, the main part of the course in hydraulics, what we're talking about in hydraulics basically is the design and operation of structures used to control this runoff. Of structures used to control runoff, okay? And these structures could vary. Some structures are aimed at containing them or storing them. So we have storage type of structures, okay? Examples of these would be detention ponds, retention ponds. Some are used to convey water, okay? So we say conveyance, okay? Conveyance would be an example that we have here in this diagram. So we have all this water arriving to this one point, and we have a highway. Wow, well, there's going to be an issue unless we build some type of hydraulic structure. And that hydraulic structure in this particular case would be a real common one called a culvert. Okay, so I'll do that. So we've got a culvert. Okay, for us to design this culvert, clearly we're going to need to know how much flow that we're expecting at this point, and so that we can design it so it can pass all this flow, okay? And so the hydrology part is used to tell us how much water we expect to get based on the watershed response and based on the characteristics of the storm itself. The hydraulics part is how do we design structures that can either store water, convey water. Sometimes we want to regulate water. For example, we're spending a lot of time in this course with regulation structures that are used in irrigation applications. When we have so much water and we want to divvy it up, so many gallons per minute to this field, so many gallons per minute to this field, and so forth, okay? So that concludes this video. Again, the highlight of this video, the most important part was we defined what hydrology is and what hydraulics is in a common everyday type of application. We talked about some of the factors that influence the storm variability. We talked about some of the factors that influence the amount of runoff that we would expect. And then we also talked about the type of information we would use in the hydraulics portion of the course so that we could design, in this case, a culvert, or it could be a similar type of structure, either for storage, conveyance, or regulation. Thank you so much.
Okay, hope it has given a good understanding about the hope it has given a good understanding about the subject that we are going to talk about. So it has several aspects in it. Share the screen again. Okay, so hydrology, as you have clearly understood from that video, is the science that deals with the occurrence and circulation and distribution of water of the earth and the earth's atmosphere. So basically in hydrology, we study about these three aspects on earth's surface: occurrence, circulation, and distribution. It is basically an applied science. The field of science has two branches. One is pure science, the other one is applied science. Most of the engineering subjects are coming under applied science. The subject is generally classified into two branches. So the subject of hydrology has two branches. The first one is scientific hydrology. And the second one is engineering or applied hydrology, this is the one that we normally concentrate on, right? So you can see this is the one that we normally concentrate on, study concerned with engineering applications of hydrology. In general, the engineering hydrology deals with these following three aspects: estimation of water resources, the study of processes such as precipitation, runoff, evapotranspiration and their interactions, the study of risk such as floods and droughts for civil engineering. Now, basically, we will be very much concentrating on this point number 2 under session 4 and 5, and point number 3 under initial sessions 2 or 3. Then we will be talking about groundwater in coming lessons. So hydrological cycle. So this is something which is fairly basic for you. You have studied this in grade 6 as well. So basically, this cycle takes place due to solar energy. That energy captured with certain molecules travel here and there and create several states of water. You can see some of them are in cloud, some of them are in atmosphere, some of them are in ground, some of them are underground. Likewise, so the water circulates in the cycle. I have studied these things, so I will not get that much depth into this. The rains comes onto the ground and part of it will run off, part of it will infiltrate, and out of this infiltration, a fraction will reach the groundwater, a fraction will flow along the gravity of the ground beneath the ground. That is called interflow. We will be talking about these things later. So in this manner, the water is circulated all around the world. Right. Rate of rainfall received. Now according to that presentation, when the rainfall is received, you can see flow over the surface will take place. Part of it will infiltrate and part of it will reach to groundwater table, and everything will finally flows into oceans, and a fraction of this will evaporates from the ground. Another fraction will evapotranspirate from plants. So this is how it takes place. So basically hydrological cycle management is governed by this equation here. This equals the precipitation equals evaporation, evapotranspiration plus surface runoff plus infiltration. So we will talk about these terms in details in coming lessons. Now, as you can see on this picture, you can see certain storages are there. These are ancient storages of water. So those are called sinks, water sinks. Now, there are several categories of water sinks: oceans, ice caps, underground aquifers mostly function as sinks to pollutants. Freshwater bodies are there, then closely interconnected forming parts of continuum from rainwater to saline water. There is a closely interconnected network from freshwater to saline water in any hydrological cycle. Now, the management of, we'll briefly talk about the management of hydrological cycle. Highly managing many of the countries for water supplies. Not like in Sri Lanka. If you go to some other countries, they highly manage this hydrological cycle because the water is a very scarce resource for industry, agriculture, and domestic use. Now, running waters generally retain in days or hours, and you can see the retention time for different type of water resources. You can see standing water in shallow lakes and deep lakes maybe in years or 100 years. But if you go to groundwater aquifers, deep aquifers, they might be contain waters for thousands of years. So the management strategy has to be changed based on the availability of water, the source of water, as well as the period of retention. Well, it continues. Then when it comes to climate change, highly affect hydrological cycle. The climate change can highly affect hydrological cycle in these three aspects. The increasing rainfall intensity, you can experience that in Sri Lanka. Now, 10 years or 15 years back, we don't have that highly intensified rains. Then prolonged drought periods. Now, when drought comes, there are months without rain, right? I'm quite sure you have experienced this in 2017, 18, especially 16, 17, 18, right? Then high evaporations, right? So due to climate change, the temperatures will go high. So as a result, the evaporation rates will increase. Results in some regions becoming wetter and some regions becoming drier. This can be experienced in Sri Lanka. So if somebody is somebody there from Ambagamuwa, Ginigathena area, Ambagamuwa Vinyathena, is there anybody? So if you are from that area, you will experience this, right? So the wetness is increasing. In certain parts of Sri Lanka, dryness is increasing, especially in the intermediate zone. Now, the fringes of Matale district experience certain water shortages during last few years. And that's the end of this presentation. So I'll move into the other presentation. So actually, with this presentation, we are going to begin the lessons, right? The important lessons, right? So in this presentation, we will talk about precipitation, evaporation, and infiltration. In fact, you will have to read about this in parallel to your course book, but unfortunately, some of you have not collected them or something has happened. So please request your regional centers to provide them to you. If not, you will have to find a way to complain it to the university, right? And what I will do is to upload the sessions that I'm going to conduct into LearnOUSL. So please follow LearnOUSL. I will be uploading these sessions. Right. Now let's begin the session 4. The analysis of rainfall data, estimation of catchment rainfall, losses and effective rainfall. Now these are the areas that is going to be covered under session 4. So as I told you, I will start from session 4 and I will continue to session 5. Then after that, I will continue from session 1, 2, 3. That is the way I am planning to finish it up to Cat 1. Now, objective of this session. At the end of this session, you will able to understand rainfall data analysis of abstractions from rainfall processes. Now, let us talk about the hydrological cycle. We were talking about hydrological cycle. Now, in this session, especially under session 4, we will be concentrating on the aspect of precipitation, mainly the aspects of precipitation. Now you can see it is covered here. Now, the precipitation measured using rain gauges, like gauges that you can see here, and the rainfall will be measured at several locations in the catchment, in the corresponding catchments. Now, when we measure rainfall at several locations, we will have to generalize the rainfall to the entire catchment in order to do modeling. So to generalize the rainfall received over a catchment, the point samplings from rain gauges needed to be generalized over the catchment. So we get point sampling at several locations. So you will have to generalize the rainfall for the entire catchment. This form of estimated rainfall is called mean precipitation over the catchment. So that form of generalized rainfall over the catchment is called the mean rainfall over the catchment. For this purpose, 3 methods are widely used. The first one is arithmetical mean method. You can see if you have n number of stations, you can accumulate all the rainfalls and you can divide by the number of gauges. So you will get the arithmetic mean here. Now, the other important method is this Thiessen Polygon method. In this method, a weighted average for entire catchment is estimated based on assigned areas for particular rain station. Steps are described in the following video. Now, let me briefly explain you a few things before you get into the video. Now, what we generally do, if you have this these points from 1 to 6 strain gauges, you have to calculate the corresponding area from the subjected catchment relevant to this each station. Let's say you take station 3, so you have to find the area of the catchment which is subjected to the rainfall which is received by the station 3. So that is found by this Thiessen Polygon method. So basically, this polygon here bounded by the catchment bounded by the polygons it gives you the subjected area for this particular station. So we calculate a weight for each rainfall at each station by dividing the area subjected to that station by the total area of the catchment. So please watch this video.
Okay, in this video I'm just going to really quickly show you how to take an area and break it up into decent polygons by using the method of basically trying to get an equal area or a representative area for a bunch of different sampling stations. So the first thing we're going to do is do an easy one, a very easy one, with only 2 data points, 2 places where the water level would be collected. What we want to do is just draw a little dotted line between the 2 stations. And if I really cared, I'd use a ruler, but this is going to be an approximation anyway, so this will do the job just fine.
So we cannot see the
Then what I
video.
want to do is do a perpendicular bisector, which basically means I'm going to find the halfway point.
You can't see the video?
Yes, sir.
You can't see, right? Wait. Sorry about that. Can you see the video now?
Yes, sir.
Okay. Right.
Okay, in this video I'm just going to really quickly show you how to take an area and break it up into decent polygons by using the method of basically trying to get an equal area or a representative area for a bunch of different sampling stations. So the first thing we're going to do is do an easy one, a very easy one, with only 2 data points, 2 places where the water level would be collected. What we want to do is just draw a little dotted line between the 2 stations. And if I really cared, I'd use a ruler, but this is going to be an approximation anyway, so this will do the job just fine. Then what I want to do is do a perpendicular bisector, which basically means I'm going to find the halfway point. And again, if I cared to pull out a ruler, I could do so, but I'm just going to eyeball it right now. The halfway point goes about there, and I want to draw a line perpendicular to that line that goes through that central point, thus perpendicular bisector. This one, because it is so simple, that's pretty much all there is to it. I'm going to go over that line, and you'll see why in the more complicated diagrams. I'm going to go over that with black. And essentially what that means is everything to the upper left side of the area is going to be closest to point A, sampling point A, while as everything in kind of the right lower side is going to be closer to point B. So anything over here in this area, anywhere, is going to be closer to B than it is to A, and likewise anything on the side of this line will be closer to A than it is to B. So this represents the area for A, and this down here the area for B. Now of course they can't all be this easy or we'd have nothing else to do in this class. So let's try just a slightly more difficult one. Let's do one that has 3 data points, or 3 sampling stations. So I'm just going to draw a quick dotted line connecting each of these 3 to each of the others. And same thing, I'm going to do a perpendicular bisector for each of these 3 points. And again, I'm pretty much just going to eyeball it. And now the pink lines I'm going to draw, I might overshoot a little bit, but that's okay. So let's do the point between A and B right here. And if I do a perpendicular bisector there, really that line is saying anything to the left of it is closer to A, anything to the right of it is closer to B. And if those were the only 2 stations, we'd be done. What we can do though is also look at the relationship between B and C. And I'm just going to draw a perpendicular bisector there. And even though I know it's not going to be used, I'll carry it on over to that left side. And again, anything above that line that I just drew is closer to B. Anything below that line is closer to C. Finally, I'm going to look at A and C and do a perpendicular bisector between the 2 of those. Just going to look something like that. And anything on the upper left of that line will be closer to A than it is to C. Anything to the lower right will be closer to C than it is to A. Now what I want to do is actually highlight a couple of those lines just to make sure that I'm representing all the areas fairly. So from here to here, I'm definitely splitting A to B. And over here, I'm definitely splitting B to C. And then finally, I want to split A and C. So I'm just going to do a line like that. Now, if you focus on just those three lines, let me actually highlight them with a slightly darker color, just so it's a little more evident. Try not to pay attention to the pink anymore, just focus on the blue. If you're anywhere up in this region, this little place isolated by this blue line and this blue line, anything on that side is going to be closest to A, closer than it is to any of the other two stations. Anything in the top right here is closer to B than it is to any of the other two stations. And anything below this blue line here, anything in this area, is all closer to C than it is to anything else. So now you can see that it got much more complicated, or at least significantly more complicated, when we went from 2 points to 3 points. Let's try one that has 5. What I'll do to try to make this one a little bit clearer is not to include all of the lines, but only the ones that are actually important. So let's take a look at points A and B, and we'll do a perpendicular bisector for those. I'm not going to extend that line all the way to the bottom, because I can already see by the time I get to about here, I'm much closer to D than I am to A. So I know that this is not going to be a line that matters. While we're at it, let's do A and D. The middle point's about there. So the perpendicular bisector there would look like this. And I could continue it over there. But again, by the time I'm over to about this area, I can see anything that I draw is going to be closer to B than it is to D. So I'm not going to worry too much about it. Let's do one between B and D. And a perpendicular bisector there. It's going to come down that way. This is going to be a little bit of an approximation. You'll notice that right around here, they don't seem to meet up particularly nicely. That has more to do with the fact that I'm not measuring these precisely or using a ruler. If it was actually done exactly properly, it was perfect perpendiculars and perfect measurements, then all three of them should meet at a point. Let's do points B and C. And we'll drop a perpendicular bisector in the middle there. And again, I'll stop drawing by the time I get too far down there, because I'm already getting closer to E. Another point between D and E. The order I do these really doesn't matter, as long as I get them all done eventually. And a perpendicular bisector there. Again, I could extend it up further, but I know that I'm already going to be into area B. And I think the last one that I need to look at, actually there's a couple I need to look at, C and E. Halfway point. Perpendicular bisector approximately. And finally, B and E. And it looks like it would be approximately here. And again, if I had done them lined up properly, they should have come to nice points instead of doing anything wonky where the lines start to intersect. So now I can break this into 5 regions. This region up here in the top left corner of the diagram will be A. B is this pentagon-y shaped region. C, the part over here on the top right. D on the bottom left, and E on the bottom right. And again, if you want me to make it a little bit more clear, I'll just go over it in blue. So that's how you do a Thiessen polygon. The truth is, doing them the first few times you do them can be quite difficult to get them exactly accurate. I'd recommend maybe doing it in pencil so that you can erase it. But once you've played with it a little bit, I think you'll just you'll be able to figure out which lines matter and which ones don't. For instance, you can see that the line I started to draw here was quite irrelevant. All it said was this is closer to A and this is closer to D, but both of them were closer to B, so it didn't really matter. If you do mess up, the biggest thing to look at is to just say, is there anything in my polygon? So let's take a look at B, for instance. Is there anything in this polygon where I think a point in there is closer to a different station? So is it possible that this is closer to C or possibly to E? And I don't think so. If you find a point that looks like it is closer to another station, it probably means that you highlighted the wrong line, and you just go back and highlight another one. Once you're done that, you've got your Thiessen polygons, and you can start calculating the area of each using the grid method. Good luck.
Okay, that's a very good video. Right. Let me share this screen. Okay, we were here, right? Now you know how to develop the relevant Thiessen polygons using perpendicular bisector. It's a very nice video. In fact, I gave a similar question to students during final examination this year. Now some of them have made a mess out of that. So please practice this, right? Now, this example you can work out in the book. It is there. Now, shall I give you 5 minutes to work out yourself? Those who do not have the book, I'll give you 5 minutes to work out this. Now, the Thiessen polygon areas are already given here. So you only need to calculate the Thiessen weight factor, then the station's reading. Then you can calculate the weighted station rainfall, and finally calculate the average overall Thiessen polygon average rainfall for the catchment. So can you do it within 5 minutes? It won't take more than 5 minutes. I'll give you 5 minutes. Please work out this. Hope you have worked out the problem. It is not that difficult. The answer is there in the book as well. Now, let us move into the other slide. Now, there is another method called Isoheital Method. Now, what we do is to create isoheitals of equal rainfalls, right? If you have set of rainfall data, you can interpolate and generate certain rainfall contours. Now, these contours represent rainfall values. So, what we do, we average, let's say, this area. Now, let's say we are talking about this area, right? Okay. Now, in this area, the rainfall can be averaged between these two adjacent isoheitals multiplied by the area divided by the total area, which is quite equal to the Thiessen polygon weight, right? But to obtain the rainfall for this corresponding area, what they have done is to get the average between two isoheitals. Similarly, you can do it for the entire catchment. You can divide the catchment between interstitial areas between two isoheitals, and you can have a series of areas. You can have series of average rainfalls. With this equation, you can calculate the overall isoheital rainfall for the catchment. Now with that, I will wrap up today's class because I will not continue into abstractions. I will start abstractions. So we were talking about precipitation. Now we have to talk about abstractions. Abstractions means the basin means water is lost from the surface runoff. So we will be talking about abstractions from the next day school. So I am thinking of having a day school on Thursday. Let's see, what is the date? Thursday is today's 22nd, 26th. Shall we have a day school around 7 o'clock? What do you say? Hello?
Okay, sir.
Is it okay for everyone?
Okay. Okay, sir.
I know there are working people. So is it comfortable for you to have a day school at around some, because we will have to do several additional day schools. Otherwise, you may not understand the subject, right? So I will arrange a day school. Can somebody make a WhatsApp group for you? WhatsApp group. No, it's okay. Right. Okay, I will arrange a day school on Thursday at 7 o'clock, and I will send you the link through Learn OUSL as well as through the common course. Okay, until then, take care. Thank you very much.